Hello, Algebra 2 students. So today we are going to practice a few more graphs of natural exponential functions, and we are also going to look at population decline with exponential growth, and lastly, continuous compounding interest. So let's start with some graphs. Now it's not necessarily easy to by hand like make an XY table for this 2e to the negative x because e is an irrational number, so we're going to get decimal point values for our y values. So instead, I'm going to have you guys graph this using a calculator or using Desmos. And what you're going to do is you're going to look for the asymptote and one important point, one nice looking point. So first, with these problems 5 through 8, you're going to see if it's exponential growth or decay. And all you have to do with these natural exponential function is check the x in the exponent. Is it a negative or a positive value? So in number 5, it's 2e to the negative x. Therefore, this is exponential decay. Next, you'll graph that on your calculator of choice. I've printed out a graph here from Desmos, and you'll see that there is a nice point that the graph goes through, and it's at 0, 2. So we will graph the point at 0, 2, and it appears that the x-axis is the asymptote, meaning like the graph is going to approach the x-axis, but never actually touch it. So we'll use that to just sketch out our graph. All right, similar process for the next 3. So in number 6, this is exponential growth because the exponent is positive. And I've graphed this on Desmos, and we can see that a fairly nice point is at 0.75. And this is exponential growth. All right, the next one, we also have exponential growth, meaning it's going to rise to the right. And the quote-unquote like nice point is at 0.5. And it is going upwards to the right. That's not the prettiest function I've ever drawn, but you get the picture. And if you're wondering, wait, 0.5, 0.75, 0.2, is it going to be a 0 and then this a value? And if you're thinking that, that's absolutely true. It will be 0 and the a value unless we're adding or subtracting something to the function, which we'll see on the next page. All right, last example here, 0.8 e to the negative 3x. We know immediately, though, that this is exponential decay, because that exponent is negative. And then the kind of nice point is at 0.8. And it is approaching the x-axis. Okay. Now we're going to do a similar type of thing. We're going to graph these functions using a calculator, or as I've done with Desmos. But then we also want to graph it and identify the domain and the range. So remember, domain is how far left and right do functions go. And for these exponentials, domain is always going to be all real numbers. And then the range is how far up and down does the function go. And there will be a restriction on the range because these functions have asymptotes. There's like a wall that they can't go past. So if I wanted to graph e to the x minus 4, one of those nice points that the graphs go through is at 0, negative 3. And that's because if you plug in 0 for x right here, you'll get 1 minus 4, which is negative 3. And then it looks like its asymptote is at negative 4. So I'm just going to draw a line down here, a dotted line for the asymptote at negative 4. because the graph is going to approach that but never actually hit it. So there's a rough sketch of our exponential graph. And then the domain and range. Domain, like I mentioned, is all real numbers. And the range, how far up and down does this go? Well, it has a bottom at -4. And it goes up for forever. So that would be -4 to infinity. Another way of writing this is y is greater than -4. I don't particularly care which way that you choose to write it. I will generally use this notation. Alright, next we have y equals 2e to the x plus 3. And the nice point that this goes through goes through 0, 5. And it also will go through -3, 2. Alright, and then it has an asymptote of the x-axis again. And there's our graph of the function. Domain is all reals. Range will be 0 to infinity. Hold on, guys, I actually think I graphed this wrong. Yes, I know what I did. Unfortunately, this graph, it just took a second for me to realize, this graph down here is 2e to the x plus 3 instead of that plus 3 in the numerator, not numerator, exponent. So really the graph of 2e to the x plus 3, you can kind of trust me on this. It goes through -3, 2, and it is increasing to the right. So it looks similar, but it doesn't necessarily go through 0, 5 like I had before. Alright, for number 11, y equals -e to the x plus 5. Domain is all reals because it's always all reals for these functions. And you can tell from the graph that it goes through 0, 4. So it goes through 0, 4 right here. And it appears to have that asymptote at y equals 5. So its range, this function has a top at 5, and it does not have a bottom, so its range is from -infinity to 5, or y is less than 5. Alright, that's really all I'm expecting for you guys as far as graphing by hand goes. So let's look at some more interesting stuff. Population decline and money, right? It's all about the money. That's what we're here to learn, right? So the population of Evans City is currently 48,500, and it's declining at a rate of 2.5% each year. You can model the population of Evans City by the equation PT is equal to PC e to the RT, where PC is the current population, PT is the population after 2 years, R is the decimal rate of decline per year. Predict the population of Evans City after 25 years. Alright, so this is an exponential growth problem. And we have the initial, or the PC, right? The initial value is 48,500. And the rate is -0.025. And the time is 25 years. So that means that the population in 25 years will be 48,500 e to the -0.025 times 25. 8,500. 500 e to the negative 0.025 times 25,960. So that would be the estimated population in 25 years. Okay. And lastly, that was, decline. Now we're going to look at growth. So this is going to be an exponential growth function. And we have the principal is 25,000. The rate is 0.098. And the time is 10 years. Right, because your parents are going to need 25,000, that's the principal, in 10 years, there's the time, to pay for your brother's college tuition. They can invest in an account with an interest rate of 0.098 or 9.8% that compounds continuously. How much should your parents invest today in order to have your brother's full tuition in 10 years? So we're just going to take the information we got from the question here and plug it into our continuous compounding equation. So A is equal to 25,000 e to the 0.098 times 10 years. And plugging that in, we should get oh my goodness, sorry guys. We want to know how much they need to put in now to get 25,000. Apologies, everyone makes mistakes. So we're solving for P. Right, they want 25,000 in 10 years. So we need to solve for P in this equation. Like how much should they put in now to get to 25,000 in 10 years? Okay, so this part right here is just a number. So we can divide both sides by that number. So I'm going to divide 25,000 by e to the 0.098 times 10 to get, let's see, 25,000 divided by e to the 0.098 times 10 is $9,382.78. So that's how much they need to invest now to have 25,000 in 10 years at that interest rate. All right, sorry for those two mistakes I made today in this problem and the graphic problem above. If you do have struggle following this because of those mistakes, please let me know, and I would be happy to go through it with you individually. Until then, see you later, guys.